Lecture 30 today. Let's see, we've got lecture 31 next Monday. The next class is an exam day, so it's not a lecture. Lecture 32, I will just videotape next Thursday for you to watch next Thursday or Friday. Then after that, we've got 6 more class periods. So that'll be lectures 33, 34, 35, 36, 37, and 38 all together. So we're getting close to the end. It's getting there. We're getting there. Just hang on. Let's do the topics for today. I want to do a quick example of the rational root theorem, actually focused on what would a textbook writer or a teacher think about when they're trying to create such a problem where you could use that rational root theorem. But then mostly it's going to be about divisibility in integral domains. And I want to weave in some kind of cool mathematical history, just like the textbook does, about Fermat's last theorem into there. I was working through reading the text, chapter 18, working on problems, preparing the lecture, working on Mathematica yesterday, and it just reignited my love of this stuff, actually. Chapter 18 is pretty challenging. It's kind of long and challenging as you read through it. It's kind of a struggle. But once you see the big picture and once you see the big ideas and the examples, I think it's really, really cool. So I'll try to get that across as well as I can here. All right, rational root theorem. First of all, again, this is not in the main body of the text, because in a sense it's not that important as far as real life, you might say, but I was taught it in high school, and I just sort of have this feeling like everybody should know it, and none of you said you knew it the other day, so evidently they're not teaching it in high school these days. And, you know, it's interesting to some degree, and it's also good for creating textbook and exam problems where you actually are trying to do some factoring. So here again is the statement. Suppose you've got a polynomial with coefficients that are integers. So it's in the ring Zx. As usual, suppose the leading coefficient is non-zero. If R and S are relatively prime, so that would mean that R divided by S is reduced as far as possible. Then if R over S, if that rational number is a zero of the polynomial, then the numerator, R, must divide A0, the constant term, and the denominator, S, of the rational root must divide the leading coefficient. Oftentimes the leading coefficient is 1, and so oftentimes in saying S divides AN, you're saying S is plus or minus 1. And you have really integer roots in that situation. Which is not always the case. Yeah, okay. Yep, all right. So, what's an example of this? How do you create a textbook or exam problem where this can be used? Well, first step is write your polynomial with rational roots, preferably third degree or higher, so it's interesting, right? So they can't just use the quadratic formula or factor easily in factored form, then expand it. The students don't see the factored form, they're trying to discover the factored form. Put it in the text or on the test and say, hey, find all the rational roots of this polynomial. Using the rational root theorem can be a pain, especially if the leading coefficient is not 1. But your work can be made easier if you use technology. So let's do an example. We'll use Mathematica here. Okay, so what do I mean? I mean, well, you could use expand. A polynomial with rational roots. And let's go ahead and make one of them not an integer. Say I make one of the factors, 2x minus 3, so that 3 halves would be one of the rational roots. Times x minus 4 times x plus 5. Oh, and for good measure, let's throw in x squared plus 1. So this is going to be a 5th degree polynomial that's going to have rational roots that are 3 halves, 4, and negative 5. It's also got complex roots, plus or minus I. You expand this, you see it as a 5th degree polynomial, and so the teacher would say, it's on the test, Suppose f of x is 2x to the 5th minus x to the 4th minus 41x cubed plus 59x squared minus 43x plus 60. Yikes. And the teacher says, find all rational roots. And factor as far as possible, perhaps, as well. Well, the R in the rational root theorem, if there, again, the rational root theorem doesn't guarantee that there are rational roots. And for a generic polynomial that comes from, say, fitting data to some polynomial curve, it's probably not going to have any rational roots. But when it does, it tells you the possibilities. R, the numerator of the rational root in the reduced form, must divide 60. Okay, there's lots of possibilities here. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 5, plus or minus 6. Where are we at here? Plus or minus 10, plus or minus 12, plus or minus 15, plus or minus 20, plus or minus 30, plus or minus 60. Yikes, lots of those possibilities. And S has to divide 2, plus or minus 1, plus or minus 2. And then you need to consider all possible fractions that you can make from these things. Okay? Which would include all those integers up on the top, and then all those integers divided by 2, which would then include some repeats. For example, 6 divided by 2 would be 3, but would include some new things like 5 divided by 2 as a possibility. That's a lot of things to check, though. And if this were an age before technology, that would be a very, well, unpleasant exam problem. Bad teacher, right? Don't put that on the exam. But with technology, it is easier than it would be otherwise because you can plot it to help you reduce the possibilities further. It's a 5th degree. It's hard to say exactly what kind of window you should pick ahead of time. Maybe you pick negative 10 to 10. And I probably should have restricted the plot range. Let me, since I don't want to keep using percent signs. I'll copy and paste this in here. Percent sign, if you never knew, refers to preceding output. Well, that made 5,000 to 5,000. So it looks like it's got 3 real roots, about negative 5, about 1, and about 4, and those abouts look like maybe they are exact, though you can't say for sure without checking. How do you check? The quickest way is with synthetic division. So you look at that picture and you say, it looks like, for example, 4 is a root. So if I set up a synthetic division, which is effectively dividing by x minus 4, by putting a positive 4 here and doing the synthetic division procedure, hopefully we should get a remainder of 0. Let's see if I can do this without a calculator here. Bring that 2 down. 4 times 2 is 8. Add, remember with synthetic division you add, you don't subtract. 8 plus negative 1 is 7. 4 times 7 is 28. Add, negative 13. 4 times negative 13 is negative 52. Add, multiply, add, multiply, add. Yay, we got a 0. The remainder is 0. That tells me x minus 4 is a factor, 4 is a 0. And I can keep going. One nice thing about synthetic division is you can just continue your diagram here. It looks like perhaps negative 5 is a root. Multiply, negative 5 times 2 is negative 10. Add, multiply, add, multiply, add, multiply, add. Get 0 again, yay! That remainder is 0. Negative 5 is a root. X plus 5 is a factor. looks like, well, okay, I sort of initially guessed maybe 1, but I know 1's not the answer, right? I know it's 3/2. Okay, if you zoomed in closer, it would be more clear that it's not 1 and possibly 3/2. So the next thing to do would be to try 3/2. Once you've done that, hopefully once more we get a remainder of 0. Bring down the 2, multiply, add, multiply, add, multiply, add. There we go. Remainder of 0 again. And again, this is now telling you the factorization. X minus 4 times x plus 5 times x minus 3/2 times 2x squared plus 2. That's one factorization. This can be written as 2 times x squared plus 1, and then you can bring the 2 through here if you like, to write that then as 2x minus 3. Okay, either way is okay. Okay, so the technology helps you narrow down the possibilities, and then you can combine synthetic division in this kind of fun way to ultimately help you factor it. And x squared plus 1, you would know, then has only imaginary roots plus or minus I, so you could not factor it anymore over the rationals. Okay. I don't know. Maybe it's nostalgia. Maybe it's I'm too old-fashioned or something. That I still think people should know the rational roots theorem. It's a fond memory from high school. We didn't have graphing calculators though. Teacher didn't give us quite as difficult of a problem. Making that a 60 was especially nasty, right? Because it's got so many factors. All right, on to the main content of the day. It's a lot of content, and it's challenging, but here's something that's going to make it easier as we go. By the way, if along the way you got a remainder that was not 0, you either made a mistake or what you guessed was a rational root was actually not a rational root. And the graphs can be deceiving. Here's something that's going to help along the way. As we go through these definitions and theorems and some proofs, think by analogy with some familiar rings. Z, Zi, Zx, and say Fx, where F is a field. These are going to be some rings that are going to be helpful to think about. I guess we can think about fields as well in general. In fields, a lot of these definitions are going to be, well, not so interesting because every noun or element is a unit. But it's still maybe helpful to think about anyway. All these things are integral domains, right? They are all commutative rings with unity that have no zero divisors. And one new example, new type of example, Z adjoined square root of D, where D is not 0, not 1. It's also what's called square free, meaning it's not divisible by the square of something, not divisible by the square of a prime. And actually, we're even going to allow D to be negative. So when D is -1, for example, it's the same as the Gaussian integers. If D is negative, we're talking about square roots of negative numbers, so this is going to involve complex numbers here. And actually, the D equals negative case is the most interesting as far as the homework and examples in the book goes. Most of you will be thinking about where D is negative. All right, you ready? Take a deep breath. Here we go. Let D be an integral domain. Elements A and B are called associates if A equals U times B, where U is a unit of D. Stop there. Writing, go ahead and write. think, okay, what are the units in these different things? Guess I'm making a chart now. IV stands for integral domain. What are the units? The units in Z are plus or minus 1. Nothing else. The units in Zi, the Gaussian integers, there's 4 of them, plus or minus 1, plus or minus I. The units in Zx, polynomials with coefficients in x, are the constant polynomials plus or minus 1. The units in Fx, where F is a field, well, let's do F first. The units in F are all non-zero elements. There could be finitely many if F is a finite field, or infinitely many when F is an infinite field. How about in Fx? The answer is all non-zero constant polynomials. Okay, now relate this to this first definition. A and B are associates. They are associated, you might say, if one is a unit times the other. In the integers, two integers are going to be associates if they equal plus or minus 1 times each other. 5 and negative 5 are associates. 7 and negative 7 are associates. 7 and 17 are not. 7 and negative 17 are not. It's an integer and its opposite that are associates. In Zi, two things are associates if they equal plus or minus 1 times each other, or plus or minus I times each other. So for example, if you got a Gaussian integer like 7 plus 5i, not only is plus or minus that an associate of it, but also plus or minus I times it. I times it, for example, would be 7i minus 5, more traditionally written as negative 5 plus 7i. 7 plus 5i and negative 5 plus 7i are associates in the Gaussian integer. They are related to each other in a trivial way, you might say, up to multiplication by a unit. By the way, if you graph these things in the complex plane, 7 plus 5i is right there, and negative 5, it's not a very good picture. 7 plus 5i is maybe right about there, and negative 5 plus 7i is right about there. And you can obtain this one from this one by a rotation by 90 degrees. And that's related to the geometric meaning of multiplication by I. Some of you may know about that, and some of you may not know about that. Complex arithmetic has lots of very interesting geometry to it. This next sentence here is pretty much the same definition of irreducibility as with polynomials over integral domains, except this is more abstract. A non-zero element of an integral domain is called an irreducible. Don't add the word polynomial because we're talking abstractly here. We're not saying over a field. There's the implicit integral domain behind things here. It's an irreducible in the integral domain if it's not a unit, and whenever you factor it as b times c, either b or c is a unit. That was the same definition of irreducibility of a polynomial over an integral domain. There's only a trivial kind of factorization. B or c has got to be a unit. This is analogous to primes. 7 is a prime. When you factor it as the product of two integers, b times c, either b or c is a unit. It's a plus or minus 1. We're allowing negative numbers in our factorizations. 7 equals 7 times 1. It also equals negative 7 times negative 1. Those would be two trivial, so to speak, factorizations. In a field, every element is an associate of every other element. restrictions on whether the element is 0 or not here. Yeah, so I guess 0 is an associate of every element. No, excuse me, it's not. Because it's an integral domain. Okay. 0 is not an associate of any element, except itself. But every other element, every non-zero element, is associated to every other non-zero element. And as far as irreducibility goes, again, every non-zero element is a unit. So every non-zero element is irreducible. Oh, excuse me, it's not, because it has to satisfy the condition of not being a unit. Okay, so we don't talk about irreducibility when the point is a few. A non-zero element in an integral domain is called prime if A is not a unit and A dividing B times C implies A divides B or A divides C. Okay, so to summarize, irreducibles can only be factored in a trivial way, and primes satisfy the same kind of condition as Euclid's lemma for the integers. Shouldn't these be the same concept, though? Why have two different words? Before we get on to that, it is true that an element A in an integral domain is a prime in that integral domain if and only if the ideal generated, the principal ideal generated by that element is a prime ideal. That's not too hard to prove. That's something you should be able to prove. You have to use the definition of a prime ideal. Here's another key to think about. A dividing some element R is equivalent to R being in the principal ideal generated by A. This means there exists an X such that R equals X times A. But that means R is something times A. It's going to be in the principal ideal generated by A. So this is pretty easy to prove if you use the definition of a prime ideal. In Z, the integers, concepts of irreducibility and primes are the same. They're equivalent. But in general, they're not. We'll see examples soon. So in this abstract setting, irreducibles satisfy the kind of definition that we typically take to primes to satisfy in the integers. And primes are things that satisfy the property that we proved back in chapter 0, that was Euclid's lemma. But now we're taking it to be a definition. Here are some basic facts from the exercises in chapter 18 that about these concepts that are worth memorizing and being able to prove. And it's not as hard to memorize these as you might think. Now again, I'm not necessarily, unless I tell you maybe for the quiz next Monday, going to say definitely memorize all these things. But I'm saying work at making them easily identifiable as true or false, I suppose. And you should be able to prove them. It's not as hard as you might think, and as far as the truth goes of these things, it's easiest, again, to think about these examples, and especially Z, the simplest example. In an integral domain, A and B are associates if and only if the principal ideals generated by A and B are the same. Think in terms of Z. If that's your integral domain, two integers A and B are associates if and only if these ideals are the same. What are associates in the integers? They are numbers and their opposites. Non-zero numbers and their opposites. 0 is its own associate. It's not associated to anything else. Plus or minus 5 are associates. Plus or minus 10. Plus or minus 17. And yeah, the principal ideal generated by 17 is the same as the principal ideal generated by negative 17. And if they're not associates, this is an if and only if, 17 and 18 are not associates. The principal ideals generated by 17 and 18 are not the same. In an integral domain, the product of an irreducible and a unit is an irreducible. Think Z. You multiply a prime number, 7, by a unit. Primes are the same as irreducibles in Z. Multiply 7 by plus or minus 1, you get plus or minus 7. It's still prime, according to these definitions. Still irreducible, I should say. Negative 7 is irreducible, just like 7 is. And again, this is going to be part of your completion homework, by the way, for Monday, these problems. And they're not super hard proofs, okay? They're a little tricky sometimes, but if you think carefully and work hard enough, you can get them in the abstract setting. Okay? And they really do help get your mind around these concepts pretty well, I think. By the way, for Monday, there's going to be no graded problems, just completion. You won't have to turn it in, so you can start studying for the exam and have a little bit more time flexibility that way too. Just completion, and they don't have to be turned in. Number 5, in an integral domain, when B is non-zero, this ideal generated by A times B is a proper, emphasis on the word proper, subset of the ideal generated by B, if and only if A is not a unit. Think by examples as far as starting to try to understand this. Think in terms of Z. This is always a subset of that. For example, if B is 7, I keep going back to 7 for some reason, and A is 8, A times B is 56, then the ideal generated by A times B is going to be, well, you could write it like this. 56Z, it's going to be all integer multiples of 56 in there. So what would that be? That would include, for example, negative 168, negative 112, 0, oops, negative 56, I forgot. Negative 56, 0, 56, 112, 168, etc. The ideal generated by 7, by B, is 7Z, all multiples of 7, and certainly the first ideal there is a subset of the second. Everything in here is in here. These are all multiples of 7. And in fact, a proper subset. And that shouldn't be surprising by this fact, because A equals 8 is not a unit. If A were a unit, if A were plus or minus 1, we would get the same ideal as what we started with. So we get the same. Proper subset, even if and only if A is not a unit. In an integral domain, being associates is an equivalence relation. A number is, or an element is associated to itself. If 5 is associated to negative 5, then vice versa, in terms of the integers, and it's transitive too. Thinking in terms of here, maybe one number is I times another, and that number is I times another. I squared is negative 1, which is another unit. They're going to be still associates. In a principal ideal domain, the principal ideal generated by an element P is maximal if and only if P is irreducible. So again, there's sort of this distinction between prime and irreducible elements, and also a distinction between prime and irreducible ideals. Maximal ideals, I should say, excuse me. Prime elements go with prime ideals, they generate prime ideals. irreducible elements generate maximal ideals. And we've seen that kind of thing before with polynomials. We were trying to create fields, remember? By doing factor rings, where we modded by a principal ideal generated by an irreducible polynomial. That should sound like something you've thought about when I say that. All right, now the content gets even more technical, but cool, I think. So we're going to think about these new examples, z adjoined square root of d. Given a non-zero integer d that is also not 1 and not divisible by the square root of prime, we consider this set, and this can be shown to be an integral domain. It's a commutative ring with unity, and the unity is the number 1, taken to be 1 plus 0 times square root of d. And this also can be proved to have no zero divisors. Okay, we've not done those proofs, but that's something we can, I think, take on faith here. So d could be 2 or 3 or 4, 2 or 3 or 5 or 6 even. We don't want it to be divisible by the square root of prime. It's not divisible. That ultimately means also it's not divisible by a perfect square. But d can also be negative. Negative 2, negative 3. And that is the main kind of example we're going to focus on, actually, is when d is negative. We can define a norm on this ring, n. It's a function satisfying certain properties, and the formula for n is this. N applied to an element of this ring, plugging this ring element into this function. The formula for it is this, which can also be written like that. If d is negative here, we are talking about these things being complex numbers in that case. And you could write them in terms of the imaginary unit I in that case as well. But we usually don't bother putting the I in there. What does this norm satisfy? Some properties that are really, really useful. Okay, and this was where I was having, besides with Mathematica, this was where I was having the most fun yesterday, is working with these properties, okay? Part A, n of 0 equals 0 if and only if the input is 0. This should be an x there, type of. N of x equals 0 if and only if x is 0. Keep in mind there that x is supposed to be something of the form a plus b times square root of b. We're just using a single symbol for it. So n of this is going to be 0 if and only if both a and b are 0. d is not 0. N of x times y equals n of x times n of y for all x and y. This is a really useful property. It's not too hard to verify. Actually, it's a bit of a pain. You just plug the numbers in and just do the algebra, and you see that this works. It's a little bit of a pain, but it's pretty straightforward. By the way, the proof of these properties is going to be number 1 on the completion homework for Monday. It's actually the first one that's the hardest. Okay? Which doesn't look like it would be the hardest, but it is. 2 more properties, C and D, and you can use property B for these. X is a unit if and only if n of x is 1. And furthermore, if n of x is a prime number, we're talking integer here, positive integer, excuse me, I should say non-negative integer, the output of this function is going to be a non-negative integer. 0, 1, 2, 3, 4, 5, 6, etc. This thing is going to equal. Can't be 1/2, for example. if that is a prime number, then X is irreducible in this ring. Almost a quiz time, hang on here. These are really useful properties. Claim, you can use these properties to, for example, prove that 1 plus negative square root of 3, square root of negative 3, I should say, is irreducible but not prime in here. There are irreducibles that are not prime in this ring. In Z, they're equivalent concepts. In the integers, primes and irreducibles mean the same thing. But in other rings, like this ring, there are irreducibles that are not primes. We'll take a quick look at the proof of that after the quiz.